Let's calculate the density of a gas, ammonia. Well, before we learned that density was mass over volume. And you look at the information, you're given neither the mass nor the volume. There is a way to derive a mathematical formula for density from the ideal gas law. Now just go with me on the derivation, and let me finish the derivation and talk about it. Some of the steps won't be obvious, especially if you haven't done mathematical derivations like this before. Well, let's divide both sides by RT. That means it cancels on the right side, and so we're left with PV over RT equals N. Let's divide both sides by volume. On the left side, volume cancels. And then we're left with P over RT equals N over V. We've only done a few steps, and it's possible that you're looking at this right now and going, so what? Okay, remember, let's go with it. Let's modify this by multiplying both sides by the same value. And we'll multiply both sides by the molar mass, italicized M. Why do that? That's an excellent question. Let's look at the right side. We have moles, N, times grams per mole. Well, that's just mass. And then divide that by volume. Well, that's density. That's mass over volume. I'm just switching sides there on the bottom right. Okay, so we have density equals, well, what remains? Molar mass times P over RT. So there's our formula. Assuming the gas behaves as an ideal gas, we can calculate the density by taking the molar mass times the pressure over the R times temperature, which is great because it shows you as the molar mass goes up, the density goes up. On the other hand, if you don't do a lot of mathematical derivations, this was a little challenging, especially the part where you multiply both sides by molar mass. It's not an easy thing to do. It is a very useful skill, though, to be able to mathematically manipulate equations and turn them into other equations. Well, in my classes, I don't require people to be able to do mathematical derivations. So how are you going to use this? Well, I'm not going to require students to use this. There's a way to solve for density without using this mathematical relationship. You can do it using dimensional analysis, just as we've been doing all term long. So how do you do that? Okay, ignore the formula. Let's just go about this as if we're doing a gas law calculation. Let's pull information out. Temperature in Celsius. You'll remember, what does temperature have to be in? Kelvin. We're given the pressure. I'll pull that out. And it doesn't seem like there's any other information. Well, there is some more information. You are told the chemical formula of the gas, ammonia. Now, that is sometimes a distractor Because if you're just doing pressure, volume, moles, and temperature, and that's it, you don't need to know the identity of the gas if it's an ideal gas, because we assume that all ideal gases behave the same. So either this is a distractor or we need it. The final units in the problem will be grams per liter. Well, since ideal gases do calculations in moles, that's why we have the chemical formula for ammonia. You need the molar mass. Because we need to convert between grams and moles. Now, as for the value of R, I'm going to use this one. I give my students 3 values of R, 1 in torr, 1 in atmospheres, 1 in bar. And so I'm going to choose the one with bar in it because of the pressure units. Now, starting this problem is a little challenging. If we're not going to use the mathematical equation, we focus on the units. And we want grams per liter. Now, if you look at the value of R, it doesn't have grams in it, does it? So, do we want liters bar over mole Kelvin or mole Kelvin over liters bar? Well, the grams per liter tells us per liter. We want liters in the denominator. So we're going to take the value of R, take the reciprocal. If you go back and look at the mathematical formula for density, it's capital M, molar mass, P over RT, over R, divide by R. Well, see, we got there without memorizing that mathematical formula. Now, dimensional analysis. Let's take care of the pressure. Multiply or divide by the pressure. Multiply to get the units to work. The temperature. Multiply or divide by the temperature. Divide to get the units to work. Now we've got moles in there, and we don't want moles in our answer. This is where the molar mass comes in. Are we going to do grams over moles or moles over grams? Grams over moles to get our moles to cancel. Now if you look at the units that remain, grams per liter, well, that's good because we want grams per liter. Multiply and divide by everything. And here's our density. It's difficult to judge if this is a reasonable value just by looking at the number. A really quick comparison, if you remember the density of liquid water at room temperature, it's about 1 gram per milliliter. Okay, now this is about 0.9 grams per liter. But the way I remember it is liquids, water, 1 gram per milliliter, gases, maybe 1 gram per liter. And it doesn't work that way all the time, but it's at least a reasonable quick check. And 4 significant figures because of the 1.013 bar. Now, how does this compare to the actual density of ammonia? Well, the experimental density under these conditions is 0.889. So the calculated value is about 2.2% too low. Yeah, that's because there are other things going on with ammonia that cause it to be more dense than what the calculated value gives, which means, is ammonia an ideal gas? Well, we're going to treat it as an ideal gas in this class, but Not always a good idea to depend only upon the ideal gas law when you're doing calculations for ammonia.